Parmentier, and we'll talk about periodic dilatonality and double-scaled SYK.
Okay, thank you very much. Good morning, and thanks to the organizers for putting together this nice workshop and for inviting me. It's my first time in Trieste. I'm very happy to be here and to have the opportunity to tell you a bit more about periodic dilaton gravity and double-scaled SYK. So this will be based on two recent papers with Andreas Blommaert, Adam Levine, Thomas Mertens, and Jacopo Papalini. So to start the discussion, we can begin with two-dimensional dilaton gravity, which is a class of toy models for quantum gravity, where besides the metric, we also have a field phi called the dilaton, which is there in order to have equations of motion that are not trivial. So in particular, we can find solutions that take the following form. Here they're written in a gauge where we use the dilaton as the radial coordinate, and the factor A that appears in the metric is related to the potential that appears in the action. And in particular, we can find the solutions that look like black holes. And one particular class of such dilaton gravities that has received a lot of attention, they consider potentials with an asymptotically linear dilaton potential. And in particular, in JT gravity, the potential is exactly linear. And this has served as a toy model for quantum black holes. And as we saw yesterday, it also can tell us something about near extremal black holes in higher dimensions. With a linear dilaton profile, the equations of motion tell us that the solution takes the form of a cutout portion of ADS2. So the dynamics reduces to this boundary dynamics, which is described, as we saw yesterday, in terms of the Schwarzian. And it turns out that the same action also governs the low energy dynamics of the SYK model, which is the quantum mechanics of N-Majorana fermions following anti-commutation relations, which are randomly coupled in groups of P fermions. So you have the Hamiltonian here, and this J is a randomly distributed coupling. The low energy density of states matches that of the dual gravitational description in terms of JT, and in particular, there's a density of states which is of the sinh square root E form. The natural question to ask is whether there is a dual gravitational description that's valid at all energies. So in order to begin to answer this question, we first need to understand the SYK model at all energies. And this can be done in the so-called double scaling limit, where we take the parameter P, which is the number of interacting fermions in each term of the Hamiltonian, as well as the total number of fermions to infinity, while keeping the following ratio, log Q, fixed. And in this limit, the partition function, for instance, can be calculated exactly. And the way this is done is by expanding the trace of e to the minus beta h in powers of h. So this will bring down different groups of such P fermions. And each group of P fermions, we can indicate them with a capital psi. And we can arrange them along a circle to indicate the cyclicity of the trace. And then by averaging over the random couplings, these guys are Wick contracted in pairs. This is indicated by drawing these chords. And then what remains to be done to calculate the trace is to commute those groups of P fermions past each other to get a -1 depending on how many fermions are in common between those different capital psi's. But in the double scaling limit, that's a quantity which is Poisson distributed with an average of log Q. So we'll get roughly a factor of Q for every chord intersection. And then one just has to sum over all these chord diagrams. But it turns out that this can be done in a smart way, as was, I think, figured out first by Bercoz and collaborators. And this is done by introducing a transfer matrix, which acts on chord states. So chord state tells you at any given time slice how many chords are present in the diagram. So here we start with 0 chords, and then at a later time slice, there will be 1 chord. And then the number of chords keeps growing. And when we reach the other side of the diagram, it's 0 again. And at every given time step, the transfer matrix tells us how new chords can appear and how old chords can disappear. And then the partition function is calculated as this transfer matrix element, starting with 0 chords and ending with 0 chords. So if we want to calculate the partition function explicitly, we need to diagonalize the transfer matrix. whose eigenfunctions are Q-Hermite polynomials. And then we get the following explicit density of states. So there is the eigenfunctions of the transfer matrix, which are labeled by cosine of theta. So in particular, there's a bounded spectrum, bounded from below and above. And then there is also the density of states, which is the measure under which the Q-Hermite polynomials are orthogonal. And this density of states takes the following form. So it's a Q-Pochhammer symbol. And it has a few interesting properties. And well, the general goal of the talk will be to find a gravitational system that reproduces this thermodynamics. So as I said, there's a bounded spectrum, but there's also a maximal entropy state because of this. So the density of state goes to 0 near the edges of the spectrum. And in the middle, there's a state of maximal entropy. In particular, this Pochhammer symbol can be expressed as the following sum. And you can see that the entropy profile will be quadratic. And it will be interesting to see whether this expansion can be given a gravitational meaning as a sum over saddles. Oh. Keeps trying to connect to Edirom for some reason. Okay. Okay. Yeah, because of the presence of this maximal entropy state, people have wondered if indeed the double-scaled SYK system could have applications to cosmology, because also in the Sitter space, empty de Sitter is a maximal entropy state. And we'll try to come back to this towards the end of the talk. So to explore a dual gravitational description, we decided to study a class of periodic dilaton gravities where the potential does not have linear asymptotics, but instead is a periodic function of the dilaton. The simplest example would be to take a sine potential, and we introduce this parameter log Q since we have in mind to eventually match with a double-scaled SYK system. And you can see here that if you take Q to 1, so log Q to 0, then we reduce to JT gravity. But we can also absorb this log Q into the dilaton so that the action looks a bit nicer. And then it appears out front as a quantization parameter, h bar. So in particular, the Q to 1 limit will be semi-classical limit, and the opposite limit of taking Q to 0 will be the highly quantum limit. One other reason to be interested in this particular version of periodic dilaton gravity is because it can be rewritten as a sum of two complex Liouville fields. And the way this is done is by introducing the conformal factor of the metric and then defining phi and phi bar as the following combination of this conformal factor and the dilaton. And the parameter B that appears in Liouville gravity is related to log Q as follows. It will be a complex, and so will be the central charges. So the central charges are complex conjugates, and they add up to 26. And this theory has also been studied from a different perspective by a bunch of people recently, including, well, the ones mentioned here. Okay, so let's begin by taking a look at classical solutions of sine dilaton gravity. So they take the general form described before in a gauge where we use the dilaton as a radial coordinate. And the factor f that appears in the metric is 2 cosine theta, where theta labels the particular solution minus 2 cosine r. So in particular, these solutions have a black hole horizon at the value of the dilaton, or at the radial value theta. And there will also be a cosmological horizon at 2 pi minus theta. And then in principle also periodic copies of these guys. Moreover, we see from the equations of motion that r equals minus 2 cosine phi. So in particular, the solutions will interpolate between ADS and DS regions. That's another reason to be interested in this theory. There's also a kind of interesting contour that will show up later in the talk. And there's a complexified contour, so over here. So we take R into the complex plane, and it has a property that along this contour, one of the Liouville fields defines a real ADS metric. So in particular, we have the sine dilaton metric, and while rescaling it, we get a real ADS metric along this contour. where the real coordinate row in the ADS geometry is related to the dilaton as follows. So this equation tells you what this contour is. And in particular, if you want to find some ADS boundary, you can find it by going off into the complex plane as such. If you want to do that, you need to introduce appropriate boundary terms. This is the Gibbons-Hawking-York boundary term, and this would be a holographic counter term. So these impose boundary conditions, which are ADS asymptotics for one of the dilaton fields and fixed length boundary conditions for the other Liouville field. Okay, so let's take a look at the semi-classical expectations for signed dilaton gravity. So if we're interested in the thermodynamics associated to the black hole horizon, the energy is again labeled by cosine of theta, as in the double scaled SYK system, but the entropy is linear. So the entropy is determined semi-classically by the value of the dilaton at the horizon. So it's linear in theta. And this is different from the double scaled SYK system, which had, as we saw, a quadratic entropy profile. What it does do is it reproduces the so-called fake thermodynamics of double-scaled SYK. So in double-scaled SYK, because there's this maximal entropy state, the temperature goes to infinity here, but the correlators still have a finite fall-off in time, and this sets the what Susskind and others have called the fake temperature. And this quantity remains finite, and it's actually the quantity that's reproduced semi-classically by a signed dilaton gravity. So with this, we can take a look at what happens in the quantum theory, and we'll follow a canonical quantization approach that was first outlined by Harlow and Jeffries in the context of JT gravity. So the phase space is labeled by two variables, which can be the ADM Hamiltonian H and the time shift on the two-sided boundaries. But we can also choose different coordinates, L and P, where L is the length of a geodesic connecting points on the two-sided geometry, on the boundary of the two-sided geometry. One technical point is that this length will diverge, so you need to renormalize it. And because of this holographic renormalization, the length can actually take values from minus infinity to infinity. And then what you do is you need to write down explicit expressions for L as a function of H and T, and then you can figure out what the canonical momentum is. And that's what Harlow and Jeffries did for JT gravity. And we'd like to do something similar here. The problem is that in general, there's not always a unique geodesic in generic dilaton gravity, but we can amend this problem by using the effective ADS metric that we saw before. So by doing this while rescaling using the dilaton, we get an ADS metric, and we can calculate lengths in this ADS metric. So this is the same as saying that we will be calculating lengths in one of the Liouville fields. And if you want, maybe an analogy is that you go to this so-called dual frame in the context of non-conformal holography, where you also do a while rescaling of the metric using the dilaton. Okay, so yeah, let's try to do this. So we already know the expression for the Hamiltonian, which was in terms of cosine theta. And then we can compute the expression for the length in these geometries as a function of theta, which labels the energy, and t, which gives the time shifts on the boundary. By looking at this expression, it turns out that this is actually the same as the semi-classical double-scaled SYK two-point function, provided that you make an identification between the length in dilaton gravity and the chord number n in double-scaled SYK. But I should stress that so far in dilaton gravity, this length is still a continuous variable, whereas in double-scaled SYK, the parameter n is a positive integer. Another surprise compared to JT gravity is that this length on the classical Lorentzian solutions is actually restricted to be positive, whereas the holographically renormalized length in JT gravity takes on values from minus infinity to infinity. And then what we have to do is we have to invert this relation to figure out the canonical momentum that's conjugate to the length, and then eliminate t and find the Hamiltonian as a function of L and P. So this will be the final result for the Hamiltonian, and we'll try to find its eigenfunctions. But this is actually, once we make the same identification that I showed before, this matches the double-scale SYK transfer matrix. But again, the lengths are still continuous at this point. It's also non-Hermitian in the same way that the transfer matrix was, but it can be brought into a Hermitian form. The only problem there is that with the square root present, it's harder to find the eigenfunctions explicitly. So we'll work with a non-Hermitian form, and there we just have to remember that the left and the right eigenfunctions are not the same. So in particular, what we need to do is we need to solve this difference equation. Yes.
So we think they're not the same is equivalent to saying that when you define, by define a cat, you need to change the contour that you've taken to some other contour.
It's saying that, yeah, there's a different inner product, I guess. There's a similarity transformation that brings the Hamiltonian into the Hermitian form.
Can you define it from the computational path?
Well, from the path integral, we don't know at this point how to define it. So I'll come back to this. So at the moment, yeah, we're doing this canonical quantization approach. Yeah, but that will be a very pressing question, how to understand it from the... Oops. Yeah, it seems like every 5 minutes, Columbia wants me to connect to Idirom. Okay, we can find a unique solution by demanding that we also solve the dual recursion relation, which is imposed by the B to 1 over B symmetry in Liouville theory. And then I can spare you some of the details, but yeah, this is what the final result looks like in more or less elementary functions. So there's these Q-Pochhammer symbols and Gaussian factors. And in particular, the left and the right eigenfunctions, they look almost the same. The only difference is that in the left eigenfunction, there's an extra Gaussian, which does not appear in the right eigenfunction. And we'll take a closer look at some of their properties next. So one important property is that they define a complete set of states when theta takes values on the real axis. And the density of states associated to them is of this form, so sine theta times the sinh. And then we can calculate the thermal partition function as a transition matrix element starting from the minimal length state, ending in the minimal length state. So here we start and end with L equals minus infinity. And what we find then by inserting the complete sense of states is the following thermodynamics. So this seems to make sense at first sight, since it reproduces the standard black hole thermodynamics, in particular the entropy, which is linear as a function of theta. However, the density of states at fixed energy really diverges, because in this way of quantizing, we needed states where theta takes on values along the entire real axis, but the energy is periodic as a function of theta, whereas this density just keeps growing. So if we want the density at fixed energy, it will get a divergent quantity. So the question is if we can find a slightly different quantization that gets around this issue of overcounting all the solutions. And in fact, this overcounting already arises at the level of the Hamiltonian, because the Hamiltonian was a periodic function of the momentum. So what we'll try to do is we'll try to do a different quantization where we periodically identify the momentum. So we want to gauge this shift symmetry. So yeah, roughly speaking, we want to divide by this infinite overcounting. So heuristically, what we might expect is that the physical states, they will be related to poles of the wave functions. And indeed, if we look at the right wave function, we see that it has poles at precisely positive integers. So this means, and I'll explain it a bit more in the next slides, but this means heuristically that we have two consequences. So the first one is kind of expected, namely that if the momentum becomes periodic, that the lengths are discretized. The second property is a bit more surprising, maybe, that there's only poles at positive integers. So not only are the lengths discretized, but they're also positive, as the chord numbers are in double-scaled SYK. So it's surprising from the point of view of this canonical quantization approach, but if you think back of the Lorentzian solutions that we had before, the lengths were restricted to be positive in the classical phase space. So that actually makes sense, and it's perhaps reassuring.
Is it also clear just because if you have the Hamiltonian on just the states that are positive integer, that have positive integer number of t, else can just never go outside of this subspace?
Well, actually,
This is a good.
yeah, there's a completeness relation for the Cure meets. That's true, but the recursion relation does allow you to go to negative. So yeah. That's right. Yeah, it truncates at this minimal length value, and as we'll see, this will also happen in more general periodic dilaton gravity. But that's exactly right. The thing is that if you use these wave functions that I showed you before, so they kind of arise from analytic continuation from Liouville gravity, then we do have these continuous wave functions that kind of leak into the negative length region. So at first it seemed like a natural attempt to do this analytic continuation, but as we saw, there are these divergences. So, but you're right, yeah, that you can. Well, if you just start with a double scale SYK transfer matrix, you might just want to quantize directly in this way.
This one thing I wonder is, in a more general case, what's the rule that tells me whether I should take one set of eigenfunctions or the other set of eigenfunctions? It seems like there are two good sets, and it's not clear to me what's the general.
Well, so I would say here in the first attempt at quantizing that maybe it's not that reasonable after all, since the density of states at fixed energy gives you a divergent answer. But yeah, after you discretize the lengths, there are no reasonable solutions. You might still try to find discretized length solutions at negative integers, but there, yeah, you can decompose them in terms of imaginary energies. Yeah, so to be a bit more precise, we're interested in the residues of this right wave function at the poles. This falls within a body of work by these mathematicians who studied the polynomial limits of the kind of wave functions that we have in our system. So in particular, the right eigenfunctions have Cure-Meet residues, and this can be seen by in this defining integral by summing over the images P, and then there will be a piece that diverges, and then the other piece that appears in front is the generating function for the Cure-Meet polynomials. And note also that there's this normalization factor, which is Gaussian in theta. So it can be absorbed in the normalization of the states, but then it would appear in the density of states and vice versa. So we can get rid of it, and it will be important. And similarly, the left eigenfunctions, they also reduce to Cure-Meet polynomials. So this is the continuous length left eigenfunction, and the dots in red are the values at integers, and these are the Cure-Meet polynomials. Again, to be a bit more precise, the explicit left eigenfunction reduces to the Cure-Meet polynomial with some normalization factor, and then again this Gaussian in theta. So a different way of phrasing this is that we want to impose a projector on physical states, which, roughly speaking, looks as follows. So there is a sum over e to the 2 pi mn, which projects onto periodic. Well, it restricts to functions that are periodic as a function of momentum, and then we divide by this infinite overcounting. So if we insert this inside the theta states from before, we're well being reduced to the poles of this right wave function, and then we know that at these values we get the Cure-Meet polynomials. So in particular, one consequence is that now the theta variables, they don't take values along the entire real axis, and we can restrict their range from 0 to pi. And the associated density of states is precisely that of double-scaled SYK. So in particular, we've kind of projected out a large number of null states, and we similarly expect a drastic reduction in the entropy. So indeed, if we now calculate the partition function, the minimal length state available is the L equals 0 state, and the partition function becomes that of double-scaled SYK. maybe to get a better idea again of what it looks like, we can put the range from theta to minus infinity to infinity, and this expression is the same as this expression. So you see it's the same as the density of states in the previous quantization up to this theta squared term, which finds its origin in the normalizations of the wave function that I showed before. And this one is responsible for reducing the entropy from a linear profile to this quadratic profile. So it seems like the entropy of these high energy black holes over here is drastically reduced. And this poses a bit of a puzzle. So it seems that this is a consequence of our canonical quantization approach, but it would be very desirable to have a path integral derivation of this in order to maybe find out what the general lesson is that can be learned from these systems. And one guess is that maybe in this way of quantizing, what we did is we secretly included some kind of observer, because it's also known in a cosmological context that including an observer can map you between this real and the fake thermodynamics. So maybe that's also what's going on here secretly. And as a first step, we can try to model this observer by inserting defect operators. So we can take a look and see what we need in order to reproduce this this partition function. So we insert defect operators which create conical deficits, and rather than just inserting one, we want to insert them weighted by a given wave function psi. And then if we take a Gaussian wave function centered around 2 pi, then the saddle point tells us that this gamma parameter will be 2 pi minus 4 theta, where theta depends on the geometry. And this then corresponds precisely to this modified thermodynamics, or the double scale SYK thermodynamics. So it would be nice to make this more precise and to do this beyond the semi-classical regime. Yeah, inserting a defect can also maybe help to understand length positivity, because now rather than just having lengths which can be arbitrarily small, if you demand that they have to go around the defect in state preparation, maybe that explains why there's a minimal length. But as I said, yeah, this remains to be made more precise. Yeah, when I said that it would be nice to have a path integral explanation, I meant at the level of the sign dilaton action. So what we can of course do is to write this Hamiltonian system that we have in terms of a path integral. And this goes by the name of the Q Schwarzian, or the Q Liouville action, which was derived by Blommaert, Mertens, and Yao. It takes the following form. So here you recognize the Hamiltonian from before. And again, we can find saddles. So there's a saddle which is responsible for the leading quadratic entropy. So this in particular gives you the quadratic entropy profile. And also this expression for the length coincides with a 2-point function in double scaled SYK. What we can do now is we can ask whether there are other saddles. And in particular, there are winding saddles that rather than begin at the black hole horizon, they begin at periodic images of the horizon. So at the same energy, we find additional winding saddles, which contribute a different entropy. So it's shifted by n. And if we also include the one loop factor, which has been derived by these people, including Jacopo, then we find actually that the double scale SYK density of states is a one loop exact sum over these saddles in the Q Schwarzian. So this gives, if you want, an interpretation of this formula that show that the beginning has a sum over gravitational saddles, in particular as a sum over horizon contributions. Okay, so this kind of concludes the first part. I don't know if there's questions at this point. Then I'll make some comments quickly about general periodic dilaton gravity, where it's harder to be as explicit, but we still expect that the main qualitative features they still hold. So in particular, we can find similar classical solutions and again do this rescaling, while rescaling to an ADS2 metric. And we can play the same game of finding the classical phase space. So again, if you look at the expression for the length, turns out that there's a minimal length state. It's not possible in general to find out the explicit expression for the momentum, but this integral representation is enough to figure out that the Hamiltonian will be periodic as a function of the momentum. And this will lead to the same type of divergences that we had before. So at the semiclassical level, this can be seen from this partition function where W, which is determined by the potential, is a periodic function of the dilaton, whereas this sinh density just keeps growing. So you can't sum over all the images. So we will try to do the same approach of gauging these shifts in the momentum to localize the wave functions on integers. And there will be, again, a minimal length state so that the wave functions are actually truncated to positive integers. And then at the semiclassical level, we expect a similar entropy reduction, which can be calculated by calculating the Onshal action of the analog to the Q Schwarzian saddle. And inspired by this one loop exact result for double scaled SYK, we might conjecture that also here the exact partition function takes the form as a sum over horizons. So you see that we also have this entropy here, and we sum over the different horizons. And yeah, it would be very interesting to see if this is actually true or not. One final comment is that all of these kind of periodic dilaton gravities, they have three universal limits. So near the edges of the spectrum, you'll find ADS JT and the sitter JT gravity. And near center of the potential, near the maximal entropy state, there will be a regime in which you describe a flat space. And we can take a closer look at this flat space regime in the explicit example of sine dilaton gravity. Yes. Because so there was this formula that the dilaton is like -2 cosine of phi, so it will be -2 around here in this linear regime, and will be +2 around here.
Okay, but the temperatures, for example, within that region look negative, just because it's.
But I think this is, but yeah, but I think this is somewhat related to this negative sign in the thermodynamics that people have talked about. Yeah, so it actually does reduce to the sitter JT gravity. Well, yeah, there are some comments at the end. I'll come back to this. Yeah, first let's take a look at the flat space case. So here we zoom in near the middle of the potential, so near the infinite temperature state, if you want. So on the left, you get the action if you still keep track of the first subleading correction. So yeah, we zoom in by taking log Q to 0, right? And then this is if you really take the full limit. So in the full limit, you really have flat space where you find Rindler solutions labeled by an energy E. But they all have the same temperature. So in particular, you get this Hagedorn spectrum that also appears in the CGHS model. If you want to get rid of this Hagedorn divergence, you can keep track of this first leading term, subleading term. And then we get almost flat metrics where R is 2 log Q phi, and we're in a limit where log Q goes to 0. So in a sense, what we're doing, if you look at the metric solutions, what we're doing is we're kind of regulating this flat space, exactly flat space case by including a cosmological horizon, which is at very large distances. So this gets rid of the Hagedorn divergence, but the partition function is still divergent because the range of energies was still in this limit from -infinity to infinity. Now this divergence is actually a remnant of the divergence that we had in sine dilaton gravity. So we know how to get rid of it there. I will also try to do it here. So here, if you take the flat space limit in phase space, you'll find the following expression. So L is related to the chord number as follows, and we also rescale the time. So then what we find from the expression for the length is that n equals e squared plus k squared with canonical symplectic form. So in other words, this system that we get in the flat space limit is just a harmonic oscillator. The difference is that what would be the position of the harmonic oscillator has a gravity interpretation as an energy, and the energy of the harmonic oscillator has a gravity interpretation as a length. And indeed, the harmonic oscillator has been studied before as a high temperature limit of double scaled SYK. Only, those people, Almeri et al., they seem to give a dilaton gravity interpretation in terms of a potential that explicitly depends on the temperature, which we thought was a bit peculiar. And here instead we have a local sign dilaton bulk interpretation. We can also take a look and see what happens at the level of the wave function. So if you try to find continuous solutions of the difference equations, you find parabolic cylinder functions. And this is also true if you start with the explicit left eigenfunction and take the flat space limit. And after this periodic identification, we restrict to integer values of n, and these parabolic cylinder functions become Hermite polynomials. So this is a plot of the exact, the psi left in black, which reduces to the parabolic cylinder function with the dotted lines in the flat space limit. And Q Hermites, they reduce to the ordinary Hermites. So the ordinary Hermites, they are orthogonal under a Gaussian measure, and the partition function that we find is then convergent precisely because of this Gaussian. There's a different limit that might be of interest, and that's the opposite limit of, rather than taking Q to 1, taking Q to 0. So that's a highly quantum limit, which suppresses fluctuations. So in particular, you get a topological contribution. And we can see how this arises at the level of the wave function. So in the Q to 0 limit, the Hamiltonian is just cosine of p, and the eigenfunctions are Chebyshev polynomials. So if you start with the Q-Hermite polynomial in the Q to 0 limit, just becomes this sum over phases, which is a Chebyshev polynomial of the second kind. And these Chebyshev polynomials, they're orthogonal with the Wigner semicircle density, which you can also find directly starting from the double scaled SYK density, taking Q to 0. Then only the two first factors in the Pochhammer symbol contribute, and this can be rewritten as a square root of 1 minus e squared. So this is also the density of states for a Gaussian matrix model. And indeed, people have discussed the relation between Gaussian matrix model and topological gravity. One thing that this might be useful for is that this topological gravity, of course, takes into account higher genus Riemann surfaces, and maybe this gives us a way to also understand how to define sign dilaton gravity on higher genus, because so far we just discussed the quantization on the disk. One guess, inspired by JT. So JT is dual to a double-scaled matrix model. So one natural guess is that once we look at sign dilaton on higher genus, that maybe we find a duality with a finite cut matrix integral. And one natural proposal would be this Q-deformed JT matrix model, which was proposed by Kohlschmeier and friends. The first step to go beyond the disk would be to figure out the cylinder amplitudes, such as the trumpet and the double trumpet or the wormhole, which encode eigenvalue correlations. And we've taken some first steps, and it turns out that also there, this polynomial reduction language of these mathematicians is kind of useful. Because this is what we do to access the cylinder. So we want to quantize the theory with end-of-the-world branes. We introduce two boundary terms into the action, labeled by mu, mu bar, and mu. And these correspond to FCCT branes in the Liouville description. And then in the semi-open channel, so where the geodesics end on the end-of-the-world brane on one side and the ADS region on the other side, the Hamiltonian that describes this evolution is now a generalization of the previous Hamiltonian, including or involving these mu and mu bar. And then by calculating a trace in this description, we can access the cylinder. So we have this two-parameter generalization of the Hamiltonian, and its continuous wave functions are known to reduce to a generalization of the Curie-Meade polynomials. And this is something, that Jacopo will talk more about on Thursday. So he'll mention these cylinder amplitudes in quite some detail. Some final comments. I can come back to, this earlier thing that I mentioned that maybe has something to do with cosmology. So there are three things that we can say here, and this is still a bit in a explorative stage, although Andreas and Adam wrote a very recent paper on this, if you want to know more. So one thing we can say is that near the upper edge of the spectrum, the theory reduces to de Sitter JT. In particular, we reproduce these results by Maldacena, Turiace, and Yang. One thing that we can note is that the divergences in the wave function that were found in the Sitter JT, they seem to be regulated in sign dilaton gravity, which ultimately goes back to there being this minimal length states and discretized length states only. Similarly, the finite, the sphere partition function no longer seems to diverge. So I won't have more to say about this, but if you're interested, I recommend this paper by Andreas and Adam. Second way in which we can try to access the Sitter physics is by interpreting the ADS contour for the Liouville field as a minus the Sitter contour. So there, the Sitter cosmology, this Big Bang cosmology, is labeled by a parameter B. And the usual no-boundary wave function would be setting B to 2 pi I. So it would be, in particular, not normalizable. What we find here is that instead of this delta function, we get a coherent state centered around this value of B. And this is also something that I think Jacopo will tell you more about, and it finds its origin in the fact that the disk amplitude decomposes as a normalizable sum over trumpets. And then finally, it's also true that in terms of the original metric, we can actually access cosmological solutions by going inside the black hole horizon. So there, the dilaton becomes a time-like coordinate. And the type of cosmologies that you get in sign dilaton gravity, or more generally in periodic dilaton gravity, are crunching cosmologies. So you start with a Big Bang, where the exponential expansion is initially well described by the Sitter JT regime, but then at some point you reach a maximum size, and at the end you crunch again. So I think we can summarize what we saw. So first of all, I described two ways of quantizing sign dilaton gravity, one of which reproduces a fake thermodynamics, and the other one reproduces the actual double-scaled SYK thermodynamics, which are distinguished by a linear entropy profile and a quadratic entropy profile. The main qualitative features, they are expected to generalize to arbitrary periodic dilaton gravity. And there's also three universal limits that I mentioned, namely ADS and DS, JT gravity near the edges of the spectrum, as well as a form of regularized flat space quantum gravity near the maximum of the potential in the high temperature regime. And then looking forward, I hope that I at least gave a flavor of the fact that this might be a rich toy model to consider, having in mind applications to cosmology. It would be very interesting to access higher genus amplitudes, of which we took some first steps by looking at cylinder amplitudes. I didn't have much time to go into detail, but Jacopo will mention this. And then the question is whether this indeed is dual to a finite cut matrix model. So that would be the reason to explore these higher genus amplitudes. It would also be very interesting to find a path integral derivation, because what we did seemed to make sense within canonical quantization. But yeah, usually in general, the path integral at least gives often some more intuitive way of understanding what's going on, or to maybe extract a general useful lesson about gravity. And perhaps also here the Liouville formulation would be an interesting way to make progress. And in particular, the language of generalized minimal models might be useful because also these have a discrete but infinite set of physical operators. Okay, and with that, thank you very much for your attention.
Any other questions or observations? Can I ask you to go back when you mentioned Mandelsena Furiachi Yang?
Yes.
I thought that there, I think a quantum correction made the wave function like finite. And but here you said that
Already in Maldacena, well, there was this recent paper by Ivo Maldacena soon, and there they also have a slightly different potential which regularizes this divergence.
your framework here, you say that divergences in wave function regulated also by quantum corrections, or just?
Well, yeah, it's well quantum in the sense that in our quantization the lengths become integer, and this eventually takes care of it. Yeah.
Okay.
Yes, I'm talking about this divergence as you take L to 0 in the wave function. Yeah. Yeah. Yeah, we can. Yeah, you can look at formulas later on. Yes. Mm-hmm.
Whether it's possibly completely off, but so there's especially recently a lot of new work in Q special functions and Q asymptotics.
Okay.
And I was just wondering if that could play a role here, talking about Sutherland analysis. In Q asymptotics, I don't mean taking Q to 0 to infinity. I take general Q from 0 to 1.
Okay.
Right? And the asymptotics. It's a very different type of asymptotics from what we have seen in other special functions.
I see. Okay, well, to be honest, I don't know exactly what you were talking about. It sounds a bit above my pay grade, but yeah, it's very possible because I mean, we also found this mathematical literature, which turned out to be very interesting. So maybe Jacopo knows more about this special functions. And
yeah, regarding your question, I think I tried to study exactly kind of problem that you are suggesting, and for instance, I think like you can go from one set of wave functions, the continuous one, to the discrete ones, through some kind of Euler summation where you take into account different non-perturbative sectors. So it's something I was trying to look into, but I still have to figure out the details. But I guess your intuition is right. So you can go from one set of wave functions to the others by including non-perturbative sectors, which in our framework would correspond to these semi-classical solutions associated with the various horizons. So it's as you're adding non-perturbative stuff to your solutions, and this can make you bridge from the continuous description to the discrete one. Yeah, we can talk about that.
Yeah, no, it's just that this is actually very new as well. Don't get me wrong. Meaning there's people nowadays going through all this Q asymptotics because the regular Borel plane doesn't quite work.
Okay.
Because the divergences are much worse in Q asymptotics. But they found different ways of finding these non-perturbative phenomena. So that's why I was wondering. So just curiosity. I'm no expert on that.
no, this sounds very interesting.
Because, for instance, I saw a lot of literature about because basically the spectral density of the continuous theory can be related to this Faddeev quantum dialogue. And basically you can relate the standard quantum dialogue to the Faddeev one through resultants. And basically the spectral density associated with the discrete system is related to a Q-programmer, so it's quantum dialogue, while the other one is related to a Faddeev quantum dialogue. So I was hoping that maybe this is the kind of resurgence that was.
I think it could be quite interesting to see. Yeah. But for me.
Yeah, for me.
Thank you for the question.
there are no other questions, then we can thank Klaas again.